Okay, let's get it started. My name is Keyan Shen, and my topic of this project is various fault tolerance schemes based on public key encryption algorithm. So what is the public key encryption algorithm? So basically, for example, you can imagine that you have two parties or more parties that they need some individual keys but combine together to share information with each other. So as you can see on the graph, if Bob and Alice they want to share some information, they want some kind of combinations of their keys to actually get the information from each other. So that's what the public key encryption mean. So I'm gonna talk about the history of it. So during the early history of cryptography, two parties would rely upon a key that they would exchange between themselves by means of a secure but non-cryptographic method, for example, a face-to-face meeting. So in 1874, a book by William Stanley Jevons described the relationship of one-way functions to cryptography and went on to discuss specifically the factorization problem used to create the trapdoor function in the RSA system. As an systematic key crypto system was published in 1979 by Whitfield Diffie and Martin Hellman, who, influenced by Raphael Merkel's work on public key distribution, disclosed a method of public key agreement. This method of key exchange, which uses exponentiation in a finite field, came to be known as Diffie-Hellman key exchange. This was the first published practical method for establish a shared secret key over a authenticated communications channel without using a prior shared secret. A generalization of Corker's scheme was independently invented in 1977 by Ron Rivest, Eddie Shermer, and Leonard Alderman, all then at MIT. The latter authors published their work in 1978, and the algorithm appropriately came to be known as RSA. RSA uses exponential module, a product of two very large primes, to encrypt and decrypt, performing both public key encryption and public key digital signature. So its security is connected to the extreme difficulty of factoring large integers, a problem for which there is no non-efficient general technique. In 1979, Michael Rabin published a related crypto system that is probably secure, at least as long as the factorization of the public key remains difficult. It remains an assumption that RSA also enjoys this security. So what is RSA? RSA is an algorithm for public key cryptography that is based on the presumed difficulty of factoring large integers. The factoring problem. RSA stands for Ron Rivest, R.D. Shermer, and Leonard Alden, who first that I just talked about just seconds ago. a user of ISA creates and then publishes the products of two large prime number along with an auxiliary value as their public key. The prime factors must be kept secret. Anyone can use the public key to encrypt a message, but with currently published methods, if the public key is large enough, only someone with knowledge of prime factors can feasibly decode the message. Whether breaking the ISA encryption is as hard as factoring is an open question known as the ISA problem. So, in my paper, I discussed the three schemes, three ISA fault tolerance schemes that can be used in many technologies nowadays. So the first scheme, the author proposes an integrated approach for both fault tolerance and digital signature in the ISA implementation. It shares the same computations required by the hash function, which is the major part of the digital signature, and the error detections and corrections. Therefore, the total overheads are minimized. The proposed approach is able to detect and correct up to 3 errors occurring in the computation processes, including encryption, decryption, and hash function evaluation in the data transmission process. So, for the single error detection and correction, the algorithm-based fault-tolerant approach is a simple and effective error detection and correction technique by pre-computing a set of checksums, which are assumed error-free in a class of computation structures. A single error can be detected and corrected. The major advantage of the algorithm-based fault tolerance are it requires less overhead compared with other fault tolerance technique. 2. It maintains the original throughput unless an error is detected. One of the problems with this is that the checksum may become too large to be represented in a computer. So in this paper, in this scheme, an approach presented based on this, it uses the intermediate results of hash function as the checksums and is able to detect and correct both computation and data transmission errors. So as you can see on the slides, for example, for given n multiply m message matrix to construct a n plus 1 multiply m plus 1 matrix xh, where h is the value of the hash function and xi and xj, x power of j are checksums, and where I is larger and equals than 1 and smaller and equals than n, and j is larger and equals than 1 and smaller and equals than m, are defined by the functions below, as you can see. So in the process 1, for a given cipher matrix xh, it will be used to compute an cipher matrix ch, as you can see here. Where Cij equals to Xij powers of Ea mod Na, Ci equals to xi powers of ea mod na, where cj powers of j equals x powers of jea mod na, and hc equals to h powers of ds mod nb for all I bigger and equals to 1 and smaller equals to n, and j is larger and equal to 1, or j smaller and equal to n. So note that all xi, xj, ci, and cj and a larger than 1 smaller than n, j larger than 1 and smaller than n are checksums and cipher checksums, and they are error-free. So the necessary and sufficient condition of a single error occurring in process 1 are listed here. When a single error in process 1 has been detected, it can be corrected by one of the following two formulas. These two. Yeah. So the process 2, suppose that there is no error or a single error that has been corrected in process 1 when user B sends the matrix CH to user A. Let CH be the matrix received by user A. So if there is a single error where CKL is not equal to CKLS, then it can be corrected by computing either one of the following two formulas, as you can see here. So process 3, to get the original messages and verify the digital signature, user A computer matrix XC from matrix CH, as you can see here, and they have some conditioning here. So under the assumption that there is error-free or an error-free has been corrected in process 2, so we have Cij equals to Cij hash for all I bigger and equals to 1, and smaller equals to n, and j bigger and equals to 1, and j smaller and equals to m, and h star equals to hc hash. If there is a single error in process 3, then the error can be defined as if CKL star is not equal to CKL power of EA mod NA, then if this equation happens, then it can be corrected by computer either one of the following two formulas here. So if there's the case, if there are multiple error detection and correction, so only so we are only gonna discuss the case of process 1 in this scenario. So in process 1, for a given n plus 1 multiply n plus 1 matrix XH, the ciphered matrix CH can be computed the same, and you have all the same condition as we just talked about in the single error detection and corrections. So if all the rest of the computation in the ith row are correct, then you can get the formula below, or the second case, if all the rest of the computations in the jth columns are correct, then you get the formula below. So that means if an error can be detected and could be corrected as long as there are no other errors located in the same row or column as this error, based on this result, claim the following statement. So there are 6 cases can be made. So as you can see, in case 1, here there are 2 errors located in the same row or the same column. As you can see, this here you have 2 errors on same row, and on this one you have 2 errors on same column. This is case 1. On case 2, there are 2 errors located in different rows and columns. Each error can be corrected in either the row or column direction. In case 3, there are 3 errors located in different rows and columns. Each error can be corrected in either the row or column direction. In case 4, there are 3 errors that are located in the same row or column. All errors can be corrected in the column or row direction. In case 5, there are 3 errors, 2 of which are located in the same row or the same column. Errors in the same row or the same column can be corrected in the column 1 row direction. The third error can be corrected in either the row or column direction. In case 6, there are 3 errors whose locations form a vertical triangle in the I to J plane. Errors in I1J1 and I3J3 can be corrected in the row and column direction. Errors in I2J2 can then be corrected in either the row or column direction. So the advantage of the proposed checksum and hash function formulas are they use the same computation unit as required by encryption and decryption in RSA, and the value of the hash function can be obtained by checksums, and up to 3 errors in the computation processes and the data transmission can be detected and corrected, and there is no overflow problem that may occur in same applications. So I'm going to talk about the problem in scheme 1. So in scheme 1, if you compute these 2 functions here and let the HC hash equals to HC, the new plain text matrix XH hash with data correcting abilities are constructed as this. So that means we can verify the validity of B signature by checking the following equation. So if these equations are true, B cannot deny having signed the forged plaintext matrix XH hash. Thus, the first scheme does indeed have a security flaw. So what does the second scheme do? So as just like the first one, they translate the message into an n multiply n plaintext matrix X, and in step 2, they also construct the n plus 1 multiply n plus 1 matrix XH, where I have all the conditions here are same. But here on the step 3, they generate the signature CC equals to C power of dB mod NB, and on step 4 say construct an n plus 1 multiply n plus 1 ciphered matrix CH star B first computes the following ciphertexts here, and then B constructs C H star as follow. So on step 5, once the user A receives the cipher matrix CH star, he or she decrypts this C star and all checksums by using his or her own private keys as follows. These functions, and then A proceed bitwise XOR operations of Cij with the hash values of CC and the indexes of matrix to obtain the plain text matrix XH here. So then A verifies the validity of B's signature by computing these two formulas and checking these. If they are true, A computes this formula and check this one. If it is true, then the signature is valid. So by this process, it can not only do error detection as in scheme 1, but also for the correction of up to 3 errors. If errors have occurred in either the computation phase or the data transmission phase, then data correction method is the same as in the scheme 1. So what is the third scheme? So in order to solve the vulnerability happens also in the first scheme, the third scheme is proposed, and it also can be used in cloud computing. So that's why you can see the step 1, the cloud network B translates the message. It's all the same as the scheme 1, scheme 2. Here the cloud network B then create a 2' number matrix P and Q, where matrix P and Q both have the same dimensions with the message matrix X, which is an n multiply n matrix. The row in matrix P are the first n prime numbers such as 2, 3, 5, 7, 11, etc. And the column in matrix Q are the first n prime numbers such as 2, 3, 5, 7, 11, etc. So the third step, this cloud network B computes a new message matrix Kx, which is the entry-wise product of matrix X, P, and Q. Hence, the row of the original message is then multiplied by a series of prime number P, and the column of original message is multiplied by a series of prime number Q. In step 4, for the given message matrix X, the cloud network B constructs an n plus 1 multiply n plus 1 matrix XH as follow, where the parameters have the conditions as here. For step 5, the cloud network B computes an n plus 1 multiply n plus 1 cipher matrix CH, which follows this condition, and know that xi and xj hash are the checksums, and ci and cj hash are the ciphered checksums. So in step 6, after download the ciphered matrix HC, user A uses his or her secret key DA to decrypt CH and obtain the decrypt message X dash H. Yeah. So I have the conclusion. which scheme 1 is the very original one that was proposed, and it's actually very old. It is an integrated approach for concurrent error detection and correction and digital signature in the RSA crypto system is presented. So as I already mentioned before, the advantage of this scheme they use the same computation unit as they require by encryption and decryption in RSA. The value of the hash function can be obtained by checksums. Up to 3 errors in the computation processes or data transmission can be detected and corrected. There is no overflow problem that may occur in some applications. So with the previous work done in scheme 1 that combined the concepts of data correction and digital signature to propose a fault tolerance scheme that is not only for error detection but is also capable of correcting up to 3 errors. It also allows the receiver to check the sender's identity. Scheme 2 shows that a malicious receiver can forge a different message for an existing signature. The sender thus cannot deny having signed the forged message. It is also proposed an improved scheme to withstand the attack. The efficiency of the improved scheme is much better than the scheme 1. So scheme 3 is also an improved scheme. It proposed grounded on RSA fault tolerance system. It has the ability to remedy no more than 3 abrupt faults. Furthermore, it permits the receiver to verify sender's identity and has a more secure encrypting method. Due to the use of permutation matrix, attacks will be forced to solve a graph isomorphism problem. Since the graph isomorphism problem are NP complete, computations cannot proceed. Thus, adaptive chosen ciphertext attacks are well defended. So that's it. Thank you for listening.